Hello everyone, I am Shubham Rai. I am going to present our work on XMG-based logic synthesis for emerging reconfigurable nanotechnologies. It's a collaborative work between EPFL and TU Dresden. In this work, we explore logic synthesis technique for emerging reconfigurable nanotechnologies. So first of all, it's important to understand why emerging and are we reaching to CMOS downscaling limit? Fortunately and unfortunately, the the scary answer is yes. Back in 2000, up till 2011, we have this kind of structure for a transistor where we have a slab of dielectric connected to the source, right? And we can see that here we have only one surface in contact with the gate terminal. Moving ahead, we then it was proposed for further uh, downscaling limits. We came up with this kind of geometry where the dielectric element was encircling it from two directions. And in this work, the author suggested that the last evolutionary step in terms of geometry can be this, where we have a stacked nanosheet or stacked nanowire kind of structure where the dielectric surrounds the individual sheets or nanowires. So yes, the answer is that we are reaching to CMOS downscaling limits, and it's important that we keep exploring certain emerging technologies which can substitute or even complement the current CMOS technology. In this work, we are more looking towards emerging reconfigurable nanotechnologies. So the overview of the work is that we will first start with uh, a few details about what are emerging reconfigurable nanotechnologies. Then we will go into why self-duality is an important concern and how it correlates with reconfigurable nanotechnologies. Then we will look into our main core of the work, the XOR-Majority Graphs, and how XOR-Majority Graph-based logic synthesis is integral for reconfigurable nanotechnologies. We will briefly discuss two major algorithms, the resubstitution, the rewriting algorithms, and then we will look into uh, experiments. Moving on, so let us try to understand what are reconfigurable FETs. So traditionally speaking, we have two kinds of complementary metal oxide semiconductors, the NMOS and the PMOS. Now they're named after the kind of charge carriers flowing through this channel. So we have the NMOS, which conducts due to negative charge carriers, and we have the PMOS, which conducts due to the positive charge carriers. In RFET, both these functionality are abstracted or encapsulated in a single device. So we have the control gate, which is analogous to the gate terminals as NMOS and PMOS, and but we have this program gate, which basically controls the kind of the charge carriers flowing through this channel. So we have the reconfigurable FETs, which can either behave as an NMOS or the PMOS. This is very well shown in this IV characteristics, where we can see that P and the N-type functionality of behavior are almost symmetrical from a single device. On the left, we have a representative figure of a nanowire FET. It can be silicon nanowire or germanium nanowire. An interesting aspect of reconfigurable FET is that it is available in many materials. Like we have silicon nanowires, germanium nanowires, carbon nanotube FETs, and even 2D devices like graphene PN junctions or molybdenum ditelluride. And ambipolarity as a phenomenon is often observed below 45 nanometers. So we tend to exploit this ambipolarity for more functionality per logic unit or per computational unit. Uh, when when we abstract this functionality of a transistor, where it can behave both as the NMOS and the PMOS, at a higher abstraction level of a logic gate, we get logic gates which have more than one functionality, which is very unlike CMOS. So you have a three-input minority, which is a very compact representation where you can have a two-input NAND or a two-input NOR. And similarly, you have a three-input XOR, which is shown here in four transistors, and it can be configured between two input XOR or two input XNOR. So we can see that that RFET based logic gates can have more than one functionality, right? Now, try to understand how RFETs and self-duality are correlated to each other. In this work, the authors have shown that the reconfigurable nanotechnologies allows efficient implementation of self-dual functions. Let us try to understand what are self-dual functions. So self-dual function is given by this two relation where f of x1, x2 till xn is equals to complement of x, complement of f of x1 complement x2 complement x till xn complement. By complementation, f of complement of f x1 x2 xn equals to f x1 complement x2 complement up till xn complement. Let's try to understand this in terms of truth table. So here we have truth table for three input XOR and or a majority, and where three inputs are A, B, and the C. Now, if we bisect this truth table into two major parts based on the value of C, but we can take any variables here. So we can have we have split the truth table in two parts. So for example, the upper part is representing a two input XOR and the lower part is representing two input XNOR. Now, what happens that in RFET, if the configuration input is connected to the program gate, there can be a simultaneous switch between the pull-up and the pull-down network for a configuration input C change. So let's try to understand this. So suppose if we consider this case where C equals to 0, B equals to 0, A equals to 0, the output of 3 input XOR is 0. Now this is only possible when the pull-up network is off and the pull-down network is on, so that the capacitance at the output can be discharged. Now let's try to switch the value of C from 0 to 1, and when we switch it, this A and B are also 0, but here the output is 1. This is only possible if A and B are 0 and are connected to a PMOS, so that the pull-up network is on and we can charge the output capacitance. And we can see that for self-dual functionality, RFETs actually helps, and the reconfigurability helps in implementation of self-dual functionality. However, self-dual Boolean functions are few. So we can see from this table that from total number of functions, the self-dual functions are very rare. So 256 functions out of 65,556 functions, and even the NPN classes are also very less. So 7 classes out of 222 classes. So this is one problem, right? We have lesser number of self-dual Boolean functions. The other problem is that RFETs in general are larger than the CMOS transistor. So in order to achieve better area numbers for reconfigurable FETs, it's integral, it's necessary that more self-dual logic must be mapped in a circuit based so that we can have more area improvements, right? So if we map all the normal logic gates to an RFET, then because of the fact that RFETs are larger than CMOS transistors, then the area would not be less. So it's important that we should map more self-dual logic functions to RFETs. So coming to this point, for the major contribution of the paper, we show that XMG's logic representation encapsulates self-duality and hence lead to better mapping with RFETs. Based on our crafted benchmarks, so these are the benchmarks which we populate, our area numbers for XMG-based logic synthesis are better by 2.46%, 1.75%, and 1.76% with respect to optimization scripts from ABC. The optimization scripts we used as compress2rs, DC2, and DCH. And over on actual benchmark suit, we get up to 12% better area numbers as compared to the same optimization scripts from ABC. And the other two important thing is that we propose two interesting algorithms: the resubstitution algorithm and the rewriting algorithm for XMGs. We also propose a filtering rule for 3-input XOR. Let's try to look into these in more detail. So the point is why we have used XOR-Majority Graphs when we have interesting graph structures and logic representations such as AIGs or MIGs. Other logic representations such as AIG or MIG can disrupt the self-duality during logic optimization scheme. XMG contain both XOR and majority nodes. Odd input XORs and majority are self-dual and hence can better encapsulate self-duality. Now let's try to understand in terms of representation. Suppose we have this function x1, x2, x3 XOR x4 in a majority relation. In terms of AIG, we need 3 plus 3, 6 plus 2, 8 nodes to represent this function. If we move to MIGs, we need 3 nodes, but the problem is that majority nodes cannot represent the parity functions in a better way. So they're not scalable. Like if you increase the number of parity functions, the number of input in the parity function, the number of majorities required increases. And if we move to XMG, so we have 2 nodes. The first function represents the majority and the second function represents the XOR. Now the problem is that in most of the logic optimization schemes, we we carry on cut-based rewriting schemes. So for example, we cut from here, we cut from here, and that actually can disrupt self-duality. So suppose if we cut from here, then the XOR functionality is disrupted, right? And hence the self-duality can be lost, which is an integral component for our area improvement. Let's try to look into the logic sense algorithm we developed for XMGs. The first is the resubstitution. Resubstitution resubstitution expresses the function of a node, which is termed here as root, using other nodes, which are termed here as divisors. We use a window-based approach with an input size of 8 to 16, so as to have scalable computation in scalable time computation. So let's take the case of this subgraph of some logic network. Here, this node has to be replaced by any other node in this transitive fan-in cone. So we first take out the maximum fan-out free cone, which is represented by this, and we see that can we have any divisors or any nodes by which we can resubstitute this root functionality. There can be 3 possible answers. So if the root is resubstituted by a constant node, if the root is resubstituted by just another replacing node in this transitive fan-in cone, or the root is replaced by a combination of certain devices. In this work, we have particularly focused on 3-input XOR-based resubstitution because 3-input XOR is a self-dual logic and it can help to maximize the self-duality within the circuit. So basically, we want to replace this function f of the root by 3 divisors ft1, ft2, and ft3, which may be available in this transitive fan-in cone. The filtering rule for 3-input XORs is required because XOR being a requires XOR being a 3-input function, it requires 3 devices, and iterating with 3 devices can be time consuming. So we use the concept of distinguishing bit pattern so as to find out only those devices which can contribute to filtering, which can contribute to resubstitution and ignore other devices. This is given by the relation distinguishing bit pattern for function f should be less than the summation of distinguishing pattern of individual devices with respect to f. So for example, if f is given by this function 1101, then and if we have these three devices d1, d2, d3, so the distinguishing bit pattern for f will be 3, the number of ones into number of zeros, and in case of distinguishing patterns for d1, d2, d3, we see that what is the distinguishing pattern with respect to the f. And we can see that in this case, the d1, d2, and d3 can basically replace the function f. Uh, Next, we move on to exact XMG rewriting. So XMG rewriting has been earlier proposed in this work, but here we improve on the existing work by taking advantage of structural hashing and supporting multiple candidates per function. We populate 4-input NPN classes for XMG. We consider a set of all k feasible cuts, and all functions are resynthesized using exact synthesis. So we have a stronger XMG rewriting technique for which can contribute to better area optimization. Now, evaluation of our crafted self-dual benchmarks. So, considering this table where we saw that the number of self-dual functionality was very less as compared to the total number of function, it is important to evaluate that whether XMGs actually uh, uh, can help to but not disrupt the self-duality within the circuit. So in order to test that, we populated benchmarks which varying number of self with varying number of self-dual nodes. So how we did that is we took four parameters: the number of primary inputs, number of levels, number of nodes per level, and SD index, and we changed the value of SD index from 1 to 10, and so that we can populate 10 variants of the same parameters of a circuit. We can, so that we can evaluate, okay, based on whatever self duality we have, what are the values we get. Let's look into the experiments. The first experiment comes out to be what the runtime improvement due to filtering. So we can see that due to filtering, due to a 3-input XOR filtering, we get an average improvement of around 52% across all the benchmark of EPFL, right? Now, the second set of benchmark, which is the main part of our work, was RFET-based mapping. What we did is we created a standard cell library with which has the area numbers reflected based on RFET-based logic gates. We use ABC as a technology mapper, and all our algorithms are implemented in the mock turtle EPFL logic sense library. So we use this as a library to see how our mapping results appear. So first we look into crafted benchmarks, where we have 10 variants of different benchmarks with different parameters, right? I took the geometric mean for all the benchmarks where the SD index is 1. So we can see that this is the initial area. This is the improvement which we get by using XMG-based logic synthesis over standard ABC scripts like compressed to RS, DC2, and DCH. This is this SD ratio, which symbolizes how much self-duality is in the circuit. As you can see that as we increase the SD index from 1 to 10, the self-duality is increasing, right? And we can see that as the self-duality is increasing, the XMG minus this improve by minus this ABC scripts, the improvement is also improving. And this is higher for DCH command, but for compressed to RS, which is kind of the most just the best optimization script as of now, which is can be considered the state of the art. This increment is like does not varies from 1.66 to 3.09%. So this is the crafted benchmarks. So this actually was done to see that whether our XMG based solutions, where our hypothesis that our XMG based solutions can maintain or maintain the can maintain the self duality is evaluated using this experiment. Next, we tried on actual benchmarks like EPFL benchmarks. Problem was with EPFL benchmark was that there were very few benchmarks with high self-duality, and the good value for self-duality is more than 50%. For example, for adder, which has a very high self-duality, but it's a very small circuit, almost all these scripts and XMG-based resistance reach to the optimum numbers. For example, for voter, which has a high self-duality, this XMG-based logic synthesis gives the best result as compared to other compressed to RS or to DCH scripts. Exception being arbiter, which has 63% self-duality, how it does not changes before and after optimization, and here the XMG is not does not work well. We will discuss the reasons for this in the later slides. So EPFL benchmarks are not very adequate or are not very representative of our hypothesis. Then we come to cryptographic benchmarks. Now, in cryptographic benchmarks, we can see that the self-duality in cryptographic benchmarks are much higher. So we can have multiple adders which have obviously higher self-duality, but again, they have the same problem that these are very small, and hence they all reach the optimal area. In case of MD5 or SHA1, SHA256, these circuits have very high self-duality ratio, so around 56%, 63%, 71%. And here we can see that there is a marked improvement using XMG as compared to compressed to RS, DC2, and DCH area, and we can get up to 12% better area numbers as compared to the previous. So conclusion is for cases where the self-duality ratio is low, mapping leads to inferior result as AIGs. XMGs are converted to AGs, and hence the number of nodes and hence the number of cuts increases, and hence we can get bad mapping. A structural biasing plays an important role here. And we can say that crafted benchmarks with high self-duality gives improved error result in case of XMG-based logic synthesis. Crypto benchmarks show 12 up to 12% better error numbers. Takeaway for future work is that experiments require better technology mapping techniques which can retain the self-duality during technology mapping phase as well. And then we can see that conversion of XMGs or MIGs to AIGs actually downgrades this part that where the self-duality can be further lost. Thanks.